All right, today we're going to be talking about section 1.2. And so we're going to go into things like mixtures, pure substances. We're going to talk a little bit about the different states of matter and kind of get into some of that stuff. So some of the basics here, all of this should pretty much be review for you. But I wanted to get you guys going here as we get started with a little bit of a catalyst. So remember, you're going to put this catalyst in your notebook. Okay, so you have taken your reading notes, and now today we're going to go through, you're going to be adding in your lecture notes and make a separate page for a catalyst if you haven't already made one, and you're just going to put all your different catalysts down on that page. And so you'll just kind of accumulate your week's worth of catalysts will just be together with your reading and lecture notes. You're going to take a picture of all that stuff and submit it. So as we start here, we want to list one physical, one chemical property of our level 1 element of the moment. Okay, so our level 1 element of the moment is this guy right here. Anybody have an idea what this element is? It's got a nucleus with a single electron moving around it. In this case, it's the representation of hydrogen. Okay, so list a physical and a chemical property of our level 1 element of the moment. And then for the physical property, okay, whatever physical property you chose, then state whether it is intensive or extensive, and then explain why that is. Okay, so go ahead and hit the pause button. We're just going to jump right in, but if you need a little time, hit the pause button and go from there. Let's talk about a physical property of hydrogen. Hydrogen is a gas, right, at room temperature. So that could have been one of the properties you were talking about. You could have talked about its color. It's not colorless. It's not colored. It's a colorless gas. You could have talked about a temperature of that gas. You could have talked about a lot of things. Now, chemical property, the biggest one for hydrogen is that it is flammable. Hydrogen is something that is going to burn. So you might have talked about hydrogen's flammability. That's probably its number one chemical property that we talk about. And then physical property. So let's say you talked about its state of matter at a certain temperature. Is that going to be affected by the amount of material, okay, or not? And so if it's affected by the amount of material, it's extensive, and if it's not, then it's intensive. So the case for hydrogen, if you were talking about the fact that it was a gas, for instance, that would not be affected by the amount of material. A lot of material, little material, still going to be a gas, and so that would be an intensive property. All right, so let's go ahead and go on to our next concept. All right, so our objectives for today, we want to distinguish between physical and chemical properties, changes, and talk about those things that make a chemical change. And then we want to look at the 3 common states of matter, and then we'll talk about physical and chemical changes. And again, like I said, we're going to touch into things like mixtures and pure substances a little bit when we talk about our states of matter as well. So what kind of changes of matter do we have? Well, we have a physical change or a chemical change. Now, the big thing that is different between a physical change and a chemical change is that when you're done with the physical change, you still have the identity of the substance remaining. Okay, so you have got this identity staying the same with the physical change. With a chemical change, you are going to change the identity. It is now going to be a different substance. Okay, so chemical change is going to change the identity. Physical change is going to keep the identity. Okay, it's not going to change the identity. So if I am changing the shape of something, changing the state of something, these are examples of physical changes. Okay, you could take a piece of paper and you could rip it, right? And that paper would still be paper. It has changed an aspect of it physically, but it's still paper, and that's the difference, okay? Chemical change, if I were to burn the paper, now that paper is no longer paper, it's now ash. It has changed its identity, and so in this case, we would have a chemical change, okay? So that's the difference between physical and chemical changes. All right. When we have a chemical change, we are going to be able to write a chemical equation for that. Okay, so you saw a little bit of that in our previous lecture, but here we've got carbon and oxygen making carbon dioxide, new substance. This is a chemical reaction, and in the chemical equation we could write C plus O2 gives you CO2. Okay, so that would be an equation for what we're seeing in that chemical change. And that's something that will happen with chemical changes. You should be able to write an equation for all of those. All right, so chemical change is equal to a reaction, right? And we will describe that with a chemical reaction, just like I talked about. The thing on the left is always called the reactants. The thing on the right is called the products. Now, you can have multiple things over here, different elements and compounds, and multiple things on the other side, okay? So reactants on the left, products on the right. However, sometimes you're going to see as we go later on in the year that sometimes we reverse that arrow, okay? And so that's where the product kind of become the reactants become the products, because the reaction can go in both directions. In some reactions, they're only one-sided. In other reactions, they'll go in both directions. So original substances are going to turn into our resulting substances. Reactants turn into products. Again, that's that formula I just showed you a little bit ago. Carbon plus oxygen gives you CO2. Okay, so that's a chemical formula, a chemical equation. Sorry. All right, so your turn, and I want you to, again, just read this, hit the pause button, try to answer it, and then we'll get right to it. So first question you're going to answer, is it possible to observe a physical property of matter without a physical change occurring? Hit the pause button, think about it. Okay, the answer is physical properties, yes, you can observe without a physical change. So I could observe something like the color of a piece of paper, or like the hydrogen, it's a gas, or something like water, it's a liquid, and it's not necessarily changing at all, right? So physical changes, yes, you can observe physical properties you can observe without a physical change. Now, chemical properties, can you observe those without a chemical change? Hit the pause button, try to answer that in your own mind. And the answer is no. The only way you can observe a chemical property, let's talk about, for instance, flammability, is if you actually get to see it changing. So when you take that hydrogen and you burn it, or you take the carbon and you burn it, those types of things are going to be changing into something else, and then you can see that chemical property because it is going through a chemical change. So chemical properties must be observed during chemical changes, okay? Something like flammability. All right, again, your turn. Why is melting a physical, not a chemical change? All right, hit the pause button, think about it for a second. And as we come into answering it, there are definitely some things that are happening here with melting that have similarities to what happens with chemical changes. In other words, there's some energy being exchanged, there's some bond interactions. However, when you are done with the melting process, you still have what you started with in terms of the actual identity of the substance. So if I take ice and I melt it and I turn it into water, it's still water. Ice and water can go back and forth through just a temperature change, and they're not changing their identity. It's still water. Water is ice and water is liquid water, right? And water is steam, vapor water. So it's not changing its identity, and that's a big difference there, okay? All right, so let's talk about our states of matter. Now, again, this is all going to be review, but we want to talk about it because now we're talking about changes of state being physical changes, right? From one state to another, so solid to liquid, liquid to gas, that kind of stuff. So we've got 4 basic states of matter that we're going to talk about. When I was in school, I only learned about 3 states of matter. They didn't even talk about plasma as a state of matter when they were teaching the concept when I was in school. The sun was made out of gas as the idea at the time, and yet now today we say, yeah, the sun's made out of plasma. So I always like to interject a little bit of that right there because science is constantly changing in terms of what we understand and how we describe things. We want to get better at describing things. So now we're talking about 4 states of matter, but a lot of scientists talk about 16 states of matter that you might be able to talk about. Well, some scientists do, there are definitely a lot of arguments for various different things being states of matter. One of the ones that's becoming more commonly accepted is one that was discovered here in Colorado at the University of Colorado in Boulder, and that's the Einstein-Bose Bose-Einstein condensate. And that is kind of a cool thing. You should check it out. It's fun to look into. And like I said the other day in the lecture, one thing that I just read this week was that they're starting to look at information being a state of matter. And I'm like, what? Huh? Anyway, might check into it. It's pretty cool. All right. So we want to talk about the solid state And you've learned this stuff before, but one of the things we might not have thought about as much is what's happening at a molecular level. Okay, so yeah, we've learned definite volume, definite shape. We've known that since like third grade. But we really want to get, in chemistry, we really want to get into what's happening in the kinetic molecular theory. We'll talk about that a lot this year. What's happening at the atomic or the molecular level when we have a solid versus a liquid versus a gas. So let's talk about the particles. Remember that the particles in a solid, what's their spacing like? What's their movement like? The spacing is that they're pretty, clumped together. Okay, they're packed in. What's their movement like? They're not really moving. There's vibration, all right, in solid shapes, in the solid state, but there's not a lot of zipping around. Okay. Then in the liquid state, matter is going to have definite volume, but indefinite shape. Okay, so again, this is what you've learned about in the past. Hey, yeah, it can change its shape, but the volume is going to be pretty consistent. However, what is it doing in the particle model? How are we thinking about it now in chemistry? How are we thinking about the spacing and the movement of the molecules? Remember, the spacing, the liquid's kind of expanded out a little bit. The movement, it's moving around faster. Now, remember, there is an exception to that, and that exception is water. Okay, water has a slightly different characteristic where its particles, as it gets into a liquid from a solid, it actually gets in closer together. But water is pretty unique in that case. Okay, so gas state, neither definite volume or definite shape. You can change its shape, you can change the volume, you can pack it, and that's something you've known about. But what is it with regard to the spacing and the movement, right? Again, want to think about spacing and movement. Particles are really spread out and they're moving super, super fast. There are particles right now that are striking your body at over 1,000 miles an hour. That's how fast gas particles move. It's very, very fast. And then we get to plasma. Now, plasma and gas are very, very similar to each other. Okay, the plasma is basically bumping up the temperature of the gas. And what happens is it gets so excited that it knocks off charged particles. It knocks off things like electrons and turns the positive nucleus into a positive charge because the electrons have left. And so when you can knock the electrons off because it's energized and moving so fast, you've hit a plasma. Now, you guys are familiar with plasma. It is the most common state of matter in the universe because all of our stars are made out of it. But it's also very common even in a room like this. Fluorescent bulbs are made out of plasma. You guys play with those little balls that have a little arc. That's plasma. You can create plasma in your microwave by microwaving a slightly cut grape that has just a little piece of skin still attached. Lots of ways to create plasma. Plasma is very common, and it's just super excited. Now, these light bulbs, these fluorescent light bulbs aren't reaching the temperatures of the sun. You don't have to have the temperatures of the sun to get a plasma. Different materials are going to reach different materials are going to reach plasma at different temperatures. Okay, so these fluorescent bulbs have mercury inside them, which get excited, and then that turns into a plasma, which gets the fluorescent bulb working. But you don't have to have super high temperatures necessarily for a plasma, although many plasmas are going to be high temperature. They're not necessarily. All right, so just a model, and again, you want to be able to create models of this kind of stuff, including the plasma, okay? And so on a test, you would want to be able to recognize these models. You'd want to be able to create these models for a lab. The one thing we would change, this is a gas, right? So you can see they're trying to represent a gas here. The one thing we would change to make that one a plasma is we would try to show little charged particles around, okay? Another thing you might be able to do when you're trying to create some of these models is you might want to try to indicate speeds by using arrows, showing that these things are moving around. Okay, again, remember the solid's just vibrating. The liquids are moving around each other. You'll notice here for water that this is more spaced out than this. Again, that is unique. Most of the time, most substances on this planet are going to be more packed in here in the solid state than they are in the liquid state, but water is unique, which is a good thing because it's what sustains life on this planet. All right, so let's talk about energy changes. Remember that whether you have a physical change or a chemical change, you are going to have an energy change, okay? There is going to be energy exchange in some way or the other. As we have something like melting, you have to heat it up, or maybe you've got something like freezing where you have to pull the energy out. And so these things are going to always involve energy, whether it be chemical or physical. You're going to have energy changes involved, okay? And it can be in various forms. You might have heat change exchanging, or it might be light that actually causes the chemical change. Some chemicals will change color once the light hits them, right? So that would be an energy exchange as well. Remember that it can be absorbed or released, but the energy is never created or destroyed, right? Law of conservation of energy is going to be in place here. Okay, so now we have gone through and we've done these objectives. In our previous lecture, we basically hit all of these things. We learned about chemistry and the properties of matter, basically on physical and chemical, and identifying intensive and extensive. So today, so far, we've kind of kicked on these last two here. Given a change description, you can identify physical or chemical. And so now we can talk about, oh, that burned, that's a chemical change. Oh, that melted, that's a physical change, right? And then we can look at those three common states of matter in terms of their particles. And we can think about them in terms of particles. That's the most important part here. How fast are those particles moving and how spread out are those particles? Start thinking like that in terms of chemistry, not so much in terms of the definite shape, indefinite volume. Still know that, but that's review. Think now in terms of this entire year, we're going to start thinking about particles and how those particles are behaving. It really helps us to understand the universe, and that's one of the things that makes chemistry so much fun to study.